What's up everybody, how's it going? In this video, we're doing the most exciting Google coding interview that I've conducted ever. That's right, this is not a Google coding interview with an adult competitive programmer, it's not a Google coding interview with a college student, it's a Google coding interview with a high school student. Not just any high school student though, this is the one and only William Lin. He happens to be a competitive programmer also. You may have seen him in his recent YouTube video that went viral where he won Google Kickstart Round A. He also represented the US at the International Olympiad of Informatics where he won a silver medal. He's also an international grandmaster on code forces. He is a veritable algo expert. Speaking of algo expert, for this Google coding interview, I asked him the hardest question that we have on algo expert. It's called airport connections. This is the kind of question that I would never expect a candidate to be able to fully solve and fully code out in just 45 minutes. I would expect them to struggle through it, to maybe get a potential solution, code out some of it. I would certainly expect to give them a lot of hints. I won't spoil anything, so you'll have to watch the entire video if you want to know how William did, but that's the question that I gave him. And by the way, on the topic of algo expert, if you're preparing for your own Google coding interviews, check out my company algoexpert.io, use the promo code CLEM, C-L-E-M, for a discount on the platform. And finally, before we jump into the interview, just a few points. Number one, this is exactly how I would conduct a real Google coding interview. You'll see that we used Google Docs, which is what you would use in a technical phone interview with Google. We also had William screen share his screen so that we could see what he was drawing. This kind of mimicked an on-site coding interview where you would have a whiteboard and you'd be able to draw some stuff. Number two, I would highly encourage you to really try to solve this problem as you watch the video. Think of how you would approach the problem. Comment down below what you're thinking, what your approach is. Number three, at the end of the video, we have a debrief session where I give him feedback. That's always good to watch because you can see how the interviewer interpreted the interview. And last but not least, number four, we actually filmed a second Google coding interview on William's channel. We're giving you all kinds of Google coding interviews. Go check that one out after you watch this video. I'll put the links in the description and in the comments below. Be sure to show William some love. He seems like an awesome guy. I had a really good chat with him before and after the interviews. Go give him some love. And with that, let's jump into the hardest Google coding interview that I've ever conducted. Hey William, how's it going? Are you ready for the interview?
Everything's going fine. How about you?
I'm doing great. I'm excited to get started.
Yep, I'm excited as well. Can't wait for this.
Okay, so we're gonna have roughly 45 minutes. We have a Google Doc. You have your own drawing app that you are sharing with me so I can see your screen, so I can see what you're drawing.
OneNote.
And OneNote, yeah. Let's begin. I'm gonna put 45 minutes on the clock starting now, okay?
Okay.
All right, so I want you to imagine that you are an airline. So you support, flying from airport to airport, and you've got a list of airports where your airline is available. And so I'm actually going to be giving you, as an input to this function that you're going to have to write, a list of airports. I'll copy it in the doc here. These airports are going to be these three-letter codes. You might be familiar with them. Like, this is how this is done in real life. So, BUD is like Budapest Airport, LGA is LaGuardia Airport, and so on and so forth. So these are all the airports that you've got at your disposal for your airline. And then I'm also going to give you a list of airport routes or airport connections. So for the purpose of this question, I'm going to use the words routes and connections kind of interchangeably.
Okay.
They're going to look like this. So they're going to be pairs. It's going to be like one list of lists of length 2, where you've got 2 airports in the lists.
Okay.
And what this represents is it means that your airline has a one-way flight from the first airport to the second airport.
One way.
So for instance here, yeah, one way. So you can fly with your airline from DSM to ORD. You can fly from SIN to CDG, etc. Okay?
Yeah.
Now, you're the kind of airline that really wants to support its travelers. You want to make sure that your travelers can travel the world, experience all of the airports that you have, connections to or flights to. And you have one airport in particular that's really popular. We're going to call this the starting airport. Maybe it's like your headquarters or something like that. So I'll put it here. This is going to be the third input to your function. And here, this starting airport is going to be LGA, LaGuardia, which is in our list of airports. Mm-hmm. You want to make sure that any traveler who wants to travel to one of these airports starting at LaGuardia can do that. You want them to be able to reach any airport in your list of airports starting at LaGuardia.
Okay.
Now, the thing is, as you might notice in the routes, LaGuardia isn't necessarily connected to every airport. In fact, I don't think LaGuardia has any outbound flights here.
Yeah, it doesn't.
It doesn't, yeah. So what you're going to have to do is you're going to have to write a function that is, or devise an algorithm that is going to determine the minimum number of routes or connections, so one-way flights, that you have to basically allow as your airline to enable any passenger to go from LaGuardia to any other airport. Now, the one caveat is that it doesn't have to be that the passenger can you still hear me? Can you still hear me?
Oh, your voice got cut off.
Okay, can you hear me now?
Yeah, I can.
Okay, perfect. So, like I was saying, you want to make sure you want to allow all of your passengers to be able to go from LaGuardia to any other airport. Now, the only caveat is that they don't have to be able to go directly from LaGuardia to another airport. It's okay if they fly through other airports. Does that make sense?
Any number of airports?
Yeah. So, for example, like imagine you could go from LaGuardia to SAN down here in the routes. That would mean that you could also go from LaGuardia to EYW because you could first go through SAN. Does that make sense?
Yes. So the passengers don't care about having like 5 transfer flights?
They don't care about having 5 transfer flights. All they care about is being able to reach the destination airports. But you have to, you're working on behalf of the airline, so you want to minimize the number of connections or routes that your airline is going to have to support so that every passenger can go from the starting airport to all of the other airports. And it turns out, just to give you the answer for this particular example here, the answer would be 3. So I'll write it down. We'll put answer 3. The reason it's 3 is because if you connect, basically like you can add 3 connections that are going to allow your users or your passengers to go from LaGuardia to any other airport.
Okay. Do you know which 3 you need to add?
Yes. So, for example, you would add 1 connection from LaGuardia to Tel Aviv, TLV, and the reason is because like that opens up a lot of flights, right? Then you would add 1 to either SFO or maybe SAN here, and then finally you would add 1 to EWR.
Okay. Okay, so that's the entire problem, right?
That is the entire problem, yep.
Oh, okay. So, first off, we have a list of like airports and like a list of like one-way connections. So you can basically formulate this entire problem as you can basically formulate this entire structure as a directed graph.
Okay.
Okay, so now, do you know about strongly connected components?
Remind me or educate me.
Okay, so imagine if we have like a directed graph. So
okay.
Maybe it looks like this. And then in this graph, we have, you might notice that, wait, actually, I'll just do this. You might notice that there are these components there are these group of nodes, okay, such that start from any node in the group, you can travel to any other node in the group. So for example, if you start at this node over here, then by like following the edges in here, you can also travel to all 3 other nodes. And
Yeah.
the same is true if you start at the other 3 nodes. You can always reach the 4 nodes. So after you find these, first of all, these strongly connected components will be disjoint from each other. So because if you imagine that, like, if we have like 2 strongly connected components where like one node is part of both, we know by the definition that like we can travel from, let's number these 1, 2, and 3. You know by definition that we can travel from 1 to 2 because they're in the same component, and then you can travel from 2 to 3 because they're in the same component. So in fact, we can also travel from 1 to 3 and 3 to 1 as well. So in fact, like if these 2 groups of nodes can all travel to each other, then like this entire group of 5 nodes is just one strongly connected component. So so what I just showed that is that these components are disjoint. So is that part clear?
Yep, that makes sense.
Okay, so after we find all of the, okay, so notice that like each node will be part of exactly one component. So if like, because single nodes will just be their own component, so each node will have its own component. And then after we do this, we'll compress all of the components into nodes. So what I mean by this is this original directed graph here will become a new graph like this. We're just basically taking the components and we're just basically taking the big circles and then like making them into the new nodes.
Sure.
Okay, so, and then in this new graph over here, the compressed graph, what this achieves is that we'll get an acyclic graph. And that's true because, for example, if we had a cycle like this, so if these 3 formed a cycle, then what would happen is that these 3 would actually be part of the same component. So it's impossible for the new graph to have any cycles.
Right. That makes sense.
Okay. So now we get to like our, oh, by the way, like we can just work with the new graph and completely ignore the original graph, because as long as we can reach some node in a component, we can reach all nodes inside the component. So
sure.
Yeah, okay, so, and then let's say that I'll just create a new like compressed graph. So if our new compressed graph looks like this, and maybe I'll just draw a few more, and then we have our starting node, which can be basically, let's say the starting node is over here. S.
Yeah, that's fine.
We'll basically add new directed edges from S to other nodes. So for example, we could do this, but then adding this edge doesn't help because like this node was already reachable from S already in the beginning.
Sure.
Okay, so now okay, so now let's so now the nodes which aren't reachable from S are these nodes over here with an in degree of 0. So they don't have any nodes pointing towards them. So it's impossible for S to reach these nodes, to reach these components.
Okay.
Okay, so it means that we need to like cover these nodes. We need to like add edges so that any person starting from S can travel to these nodes, right?
Yep.
Okay, so the only way we can do that is if we add an edge from somewhere connecting to like this node over here. And then we need to do the same thing for this as well. And then notice that if these two nodes within degree 0 are reachable from S, then that means that all other nodes will also be reachable from S as well. As long as we cover the nodes within degree 0, then we'll be fine.
And just to clarify, William, when you say in degree 0 or n degree 0, you're talking about like inbound edges, right?
Yeah, like in degree is inbound edges, and then out degree is outbound edges.
Yep. Okay.
So we know that we must at least add an incoming edge to each of these two nodes in order to like satisfy the problem. And one way you can do so is just to connect it to S. So we'll just connect them like this. And then after we connect a new edge from S to each node within degree 0, we will be able to like all nodes will be able to be reached from S.
Yeah.
Okay, so the answer for the problem will just be the number of nodes with an in degree of 0 which are not S. So in this case it's just 2. And so the entire algorithm here is, so first, I'm on the Google Doc right now, by the way. So
yep.
the first thing we do is we'll process the input. So we'll make the strings into some more usable form, I guess. So
okay.
And then we'll we'll find the strongly connected components. Okay, and then next step is to compress the graph based on components. And then last step is find number of nodes with in degree equals 0, which are not S in the new graph. And then that'll be our answer.
And just, William, for the number, that last step, the number of in degree equals 0, which are not S in the new graph, is it not possible to have two nodes with in degree 0 that then connect the same node? It is possible, but those two nodes would still have in degree 0, so you would still need to reach them. So actually disregard what I just said.
Yeah, so we know that like we must connect these type of nodes, and then it happens that once we connect these type of nodes, all nodes will be reachable. So we establish the lower bound and the upper bound for the answer to be this number, the number of nodes with an in degree of 0 which are not S.
Yeah.
Okay, so should I?
So if you want, why don't you, before you jump into the code, why don't you just very briefly walk me through like how you are gonna conceptually do these 4 steps?
Okay, so processing the input, I guess. So first, I'll just go through the list of airports and then assign each string an ID number for the airport starting from 0. So
okay,
0, 1, and then And then what I'll do is I'll create an adjacency list to represent the graph. So for each of these, I'll have a map which stores the string and an integer, and then this will be the map which converts from the name of the airport into the ID of the airport. And then
Sure, sounds good.
I'll go through the list of routes, and then for each route I'll convert the name into the ID. And then right, so first what I'll use to store the graph is I'll use an adjacency list. So basically a vector is just a list, and then I'll have, so for each of the n nodes, I'll store a list of which nodes it can reach.
Yep.
Example, let's say DSM, if DSM is 0 and ORD is 1, then what I'll do is I'll just add the value 1 into adjacent 0. Is that?
Yep.
Okay.
Totally, yep.
Okay, so now I created the adjacency matrix. No, the adjacency list of the entire graph. And yeah, that's basically what I wanted to do in the input.
Yep, sounds good.
Based on the adjacency list, I will find the strongly connected components. So this is the more I guess this is the more interesting part of the solution. So there are actually algorithms which do this for you. I think it's called Kourasagi's algorithm, and it'll basically it'll give you the strongly connected components of a graph in O of n plus m time, where n is the number of nodes, or the number of airports in our case, and m is the number of edges, or the number of routes in our case.
Sure.
So, should I explain this algorithm? Like, I don't exactly know how to, don't really exactly know how to explain it. I just kind of know it.
If you want, for now, let's skip it, and once you get into the implementation details, maybe we'll talk about it there. But the idea is here, you're applying this algorithm to get all of those strongly connected components. And I'm assuming, is the idea that your output there will be another adjacency list, but for just these new connected component nodes, or what?
Guess the output will be, so for each, so I guess for each component, we'll choose a representative node of the component arbitrarily. So maybe
okay,
these are the representative nodes of each component, and then what we'll do is basically have this array called who of u. Basically, who of u will return the node, which is the representative node of its components. So, for example,
sure, okay,
I call it, if I want the who value of this node, then it'll return this node because it's the representative node of its component. And then,
gotcha.
Yeah, okay. So this algorithm should return it should create this who array.
Yeah.
Third step is to compress the graph based on the components. So, alright, so what I'm going to do is, in order to represent the new graph, I'm also going to use a new adjacency matrix. I'll call it adj2 of n. And then even though there might not be n components, I'll still have an array of size n. And then what I'll do is I'll only consider the representative nodes. So basically all nodes u such that who of u is equal to u. These are the nodes that like I'm going to work with.
Okay.
Okay, so in order to get this new adjacency list from the old one, well, what I'll do is like basically for each original edge u to v, if these two are from different components, then I'll basically add a new edge for their representative nodes. Does this part make sense?
Can you repeat that? So for every you'll go back through every.
Right now I want to. Yeah.
No, go ahead. You go ahead.
Okay, so basically, for each of the original edges in this graph, I want to add these edges, convert these edges into the new graph over here. Okay?
Yeah.
Okay, so the first thing is if an edge connects two nodes in the same component, then since the component just becomes one node, then we'll just remove this edge. So
sure.
That's what I do here. So for each edge from u to v, if u and v are not in the same component, and we can check that they are not in the same component if they have different representative nodes.
Right. Oh yeah. Okay.
Okay. So if we find that u and v are from different components, so like these two nodes, then we'll add an edge in the new graph between the components. So
gotcha.
And then so that's why we add an edge from the representative node of u to the representative node of v.
And just if you go back to your drawing for a second, here in the upmost connected component, the one that you were looking at a second ago, you have that one with the 4 nodes. Imagine 2 of those nodes pointed out to like that other green node in the one with the triangle. How would you handle like not counting twice, that the representative node of the 4-person thing points to the representative node of the 3-person one? Does that make sense as a question?
Do you mean like another edge like this?
Yeah, exactly. How would you, and imagine that other edge that you pointed, imagine it pointed to, yeah, I guess yes. Because that means that you would add the representative node potentially twice. How would you handle that?
Okay, so if we have 2 of the same edges in this new adjacency list, then it actually won't affect our answer because our answer is just the number of nodes with an integrity of 0, which are not s. But then if we add if we duplicate edges, then that won't change if a node has an integrity of 0 or not.
I see. So you are purposely okay with duplicating edges.
Yeah, and it's not purposely, it's just convenient to not check for duplicates.
Fair enough. Yep. Nope. Totally makes sense. Okay.
So now we have this, now we created this new adjacency list. And what we do is, now the only part left is to find the number of nodes with an integrity of 0, which are not s. So the first step, I'll just go through count number of u such that, so I only want to work with the representative. So first thing is you need to make sure that u is the representative of the component, of its component, and then you also need to make sure that it has an, oh, so actually after we create the new adjacent list, C-list, let me think. So since,
yeah, no problem, take your time.
Okay, so since we want the in degree of all the nodes, what will make more sense is instead of having, instead of like working with a new adjacency list, we actually just need to count the in degree for all of the components. So I'll just have an array here called degree. So then our code doesn't change much. What we'll just do is, we'll just change this part. So we add an edge in the graph from u to v, and when this happens, the in degree of v increases by 1. So I'll just replace this part with, I'll add 1 to the degree of the representative node of v, like this.
Gotcha.
Okay, so now,
so for instance, in your one node here, you have in the one with the 3 nodes in it, you would suddenly have an n degree of 2.
Yeah. Okay.
Gotcha. Okay.
So now we want to find the number of in degree which is 0. So we just check that it's 0, and then after we find that count, we just and we just need to make sure that it's not the component of s. So as long as this component does not contain s, then we'll count it, and then the count will be our answer.
Yep.
Okay.
Okay, I think this is a good like overview of everything. I think we can jump into the coding. We've got like roughly 15 minutes left, so yeah, let's jump into it.
Okay, so I guess I'll just write a function for this. So actually, I'll just not care about capitalization.
Yeah, don't worry about that.
Just call it solve, because I don't know what to call it, and then I'll have a list of airports. So be a list of string. Then I also have a list of strings, which will be the routes. And lastly, I have the starting airport, which is a string.
Yep.
Okay, and then, so first step, I go through the list of airports and assign each string an ID number. So to start with, I'll just find n, which is just size of list of airports, and then I also have this map to convert from each string of the airport to its ID. And I just go through each of the airports, and then I'll set the string. I'll put an entry in the map with the string as the key and I as the value, and I will be the ID of the airport. Okay, and then I create this. Actually, I'll just do this kind of like in competitive programming. So I'll have a maximum value of n. I'll just make it something like this, and then I need to declare this adjacency array on the outside with the max
Okay.
value of n. So this part is still okay, and then I go through the routes. Actually, I'll just do this. So for each edge, I'll just add it into the adjacency list. So
Okay.
the starting node will basically be, I'll basically use my map to find the ID of the starting node, which is the first node of this list. And then I'll find the ID of the second node. And then this will basically add the edge.
Yep.
And then the second part is running the strongly connected components algorithm. So for this, I'll need it gives me a who array. So I'll declare this as well. And then for the algorithm, for this algorithm, I also need a reversed adjacency list. So I'll call it RJ.
Okay.
And then I also need, what is it? I need a stack for this. Okay, and then in the start of the algorithm, I'll create the reverse adjacency list. So basically, for each edge in the adjacency list, I'll just add it to the reverse adjacency list. I'll just swap I and j to make it reversed.
Right. Okay.
Okay, and then the algorithm consists of two parts. The first part is like, oh yeah, and I also need a Boolean array to store if I visited a node or not, for the DFS that I'm going to run.
Okay.
Okay, so if this node is not visited, this node is not visited, then I'll run DFS on it. So let me write the code for DFS1. So when I visit this node, I should set it to visited, and then what I'll do is I'll try to visit other nodes from this node. So for each other node in the adjacency list, if it's not visited already, then I'll visit it. And then lastly, I need to add this node into a stack. Okay, so that's the first DFS function.
You're adding the node that you are currently doing DFS on in the stack?
Yeah, after I visit all other nodes.
Okay.
Okay, and then the second part, I basically go through the stack starting from the top of the stack. So while like the stack is not empty, look at the top of the stack, and then I'll remove it. Okay, and then so what I'm going to do here is, actually I'll just create a new array called viz2. So this will act the same. This will have the same function as the first viz array, but then it'll be for DFS2.
Okay.
And then if it's not visited, then we'll visit it like this. And then now, remember that we need to find the who array. Like this node u here will be the representative node of the entire component. So what DFS2 will do is DFS2 will go through all nodes in u's component, and it'll set those nodes to, it'll set the representative nodes of all those nodes in the component. So
to you.
Yeah. Did you say something?
No, I said, I just confirmed what you said. Yeah, to you.
Okay, yeah. And this will be the representative. So since we visited, we set it to visited, and then we set the who array. So we set it to the representative. And then at this time in DFS2, we work with the reversed adjacency list. So we do pretty much the same thing. And then if V is not visited, then we'll visit it. And this time we go to node V, but then the representative is still the same. So we call DFS2 V and rep.
Is the reason that you are going through the reversed adjacency list here? I guess, like, what is that reason?
The reason is with how this algorithm for finding the components works. So, I haven't really thought much about why this algorithm does this, but if you want me to, then I can try to find a few examples.
Let's assume for now that I trust that it works. Just interesting. And I'm sure that there's a piece of logic that then makes everything click together. But okay, let's assume that it works.
Okay. So now after this entire loop of 2 DFS, we basically found the who array for each node. So now for this problem, we can just ignore the new adjacency list. We only need to work with we only want the in degree of all of the nodes. So
yep,
I'll create this array called, I'll just create this degree array, and then let's see. So yeah, we go through the edges. And then what we do is we check that these two are in different components, and if they are, then we add an edge from who of I to who of j. So the in degree of who of j increases by 1. So this will give us the in degree of all of the in degrees of all of the nodes in the new graph.
Yeah, because if they don't have the same representative node, then the one that we are pointing to has an in degree. Okay.
Yeah. And then last step, we found the degree array. Now we just count the number of nodes, number of components with a 0 in degree and don't contain S. Okay, so this will be our answer. So we go through each of the nodes and first check that it's a representative node, so who of I should be itself. And then you also check that it has a degree of 0. So now we make sure that it doesn't contain it doesn't contain S. So as long as I is not equal to the who of the ID of S and the who of ID of S, I'll just use the map to find the ID. So it's starting airport. Okay, so if all these 3 conditions are true, then that means we need to add an edge from the starting airport into this node. So we add 1 to the answer. And
can you repeat why you're doing the first condition, the who of I equals I?
Oh, okay. So I'm basically iterating through all nodes in the original graph, like from 0 to n minus 1. But then what I want to do actually is to iterate through all nodes in the new graph.
Oh, the condensed graph.
Yeah, the condensed graph. So those so in order to iterate through only the nodes in the condensed graph, I make sure that the node it's representative in its own component, since each component has exactly one representative. So each component will be checked through exactly once.
Gotcha, I see. So this condition sort of like cleverly ensures that you're only going through those representative nodes.
Yes.
Gotcha. Okay.
Okay.
Cool. So it looks like you're done here, right?
Yeah, it's in, yeah, I'm pretty sure it is.
Okay, so before we've got like a couple minutes left on the clock, which is like kind of perfect timing. Let's see if we can just if you can walk me through all of the various like code blocks and their complexity analysis.
Oh, okay. So, oh yeah, I forgot to do that. Okay, so the first part, and by the way, for map, again, C++ map, it's basically a binary search tree. Its operations are like O of log n. Like, if I want to improve the operations to constant time, I can use a hash map using an ordered. But I didn't like really care about this, since this is just, it doesn't really matter in this to making the solution correct. Anyway, so in order to improve the complexity, I'll just use an ordered map here. Okay, so the first part, this loop, oh, by the way, I'll just use n as the number of airports and m as the number of routes or edges. So this is O of n. This part is O of m because we loop through m times each iteration is constant time. And then for creating the reverse adjacency list, this part is O of n plus m, because we loop through, we have n iterations, so that creates the n here. And then also for each we iterate through each of the edges, so each in the graph like gives us constant time. And then for this DFS, this DFS is O of n plus m time. This is pretty similar to like a normal DFS. So what we do is, since once we visit a node, we never visit again. We visit each node exactly once. So that gives us like the n in our time complexity, and the m comes from, so every time in this loop over here where we go through the adjacency list of u, we do this exactly once for each edge. So each edge is checked exactly once. So that gives us O of m.
Gotcha.
And then this part with the second DFS here is, it's pretty much the same thing as the first DFS. Do I need to explain it?
This is where we get into the whatever you called Korolaju's algorithm or something.
Actually, like, I'm just saying that the second DFS is like structurally it's
the same as the first one. Yeah.
So time complexity is the same.
Yep.
And then for this for loop here, where you calculate the degree array, we loop for I from 0 to n, and then we also loop through all of the edges. So this part is, and each edge we loop through gives us constant time. So this part is O of n plus m. And then lastly, for counting the answer, we we loop through all n nodes, and then each node is we do a constant time check. So this part is just O of n. So in total, like if we add everything together, we get a time complexity of O of n plus m.
Yep. Cool. And let's skip the space complexity for now. Just in the T minus like 3 minutes that we are in now. Just one quick thing that I'm curious about. Here in your while loop,
yeah,
you're popping off the stack once, but then you repop off the stack. Why are you doing that second popping off the stack?
Oh, actually, the top, this function top doesn't pop off the stack. It only...
Oh, it's top.
Yeah.
Top, okay, yeah. I thought it was pop. I misread.
Okay.
Okay, cool, perfect. Okay, so then this makes more sense, and I think this looks great.
Yeah,
I mean,
as long as...
We're out of time.
Oh, okay.
Oh, say again?
As long as I didn't, like, mess up my implementation for Kurosawa's algorithm, then this should be fine.
Yeah, I mean, I'm gonna look that up, and at this point, we're done with the interview. So I think, you know, for the people who are still watching here, I would encourage you to look that algorithm up. I'll probably put it on the screen somewhere. I'm gonna go look it up. I'm curious, especially like why you're doing the reverse adjacency list. So okay, let's get into debrief if you want, like William, just since for the rest of the video. So. First of all, this went a little bit over time. It went to like 48 minutes, but like this was like totally fine. I will do my best to give like feedback for whatever feedback I can give. But first of all, like this went splendidly. Like seriously, like this is awesome. Like I said at the beginning of the video, like this is the type of question that I would either not ask in an interview because I think it's too difficult in an interview or too time consuming or both. Or if I were to ask it, I would not be expecting like perfectly written code or working code, and I would probably be expecting quite a few hints. So fantastic job from the point of view. Oh, sorry, go ahead.
Oh, yeah, I wasn't expecting strongly connected components in this problem because it's actually a fairly it's pretty common in competitive programming, but then it's not common enough to actually be in coding interviews. So I was kind of surprised.
It's a fairly complicated, yeah, I'd say it's like probably like a slightly more advanced graph topic. You can solve this with a worse complexity without doing the connected components. And I was actually like, I didn't think of the connected components solution, where I've thought about it, but I've never really like written it down. So this was like super cool to see. Cause you can basically do like more DFSs to find like unreachable nodes or things like that, which give you the same answer, but are not nearly as elegant as condensing the graph, if that makes sense, right?
Yeah.
But so, yeah, going back to just the feedback, like from the algorithmic point of view, fantastic job. Like there's probably no point of criticism that I can give you. You not only were able to solve the problem clearly optimally, but you went through it seamlessly. From a communication point of view, really great job. Like you're under pressure, you're writing a really complicated algorithm, you have to write the code. Like I was not lost at any point in time except for my own lack of knowledge about like the Kurosawa's algorithm. So I was able to follow through what you were doing, which is like, I think it is, I'm commending your ability to communicate here. Mm-hmm. And then finally, as far as the code, I mean, if I want to be like really nitpicky, but really keeping everybody watching, and you too, William, like this is, I'm trying to find constructive criticism. I would just say that, you know, in coding interviews, typically we prefer seeing a little bit more descriptiveness in like the variable naming because it helps, you know, follow through. I think this is something that like in competitive programming, you tend to use like very small variable names, right?
Yeah, I guess. Yeah, that's true for competitive programming, but I guess like, I thought since I was already like, talking through what my code was doing. So I thought it was fine if I didn't use variable names, which were that descriptive?
I would say it was, because like I said, I didn't, typically like the reason you look for descriptive variable names is because it helps make it easier to follow, but I had no problem following here because you were communicating so well and you went through the examples so well. So yeah, I think, yeah, they were all good. And also things like adjacency or degree or edge, UV, these are totally fine. Maybe who would have been like, you know, maybe there was a point of improvement, but like, again, I'm really being, trying to find constructive criticism, but otherwise, fantastic job. Without a doubt, strong hire from my point of view, if I were like a coding interviewer at Google still. For both an internship, like not even a question, and full-time, not even a question too. So for what it's worth, William, you have Clement Mihalescu's blessing for whatever that represents.
Yeah, it really, I guess, it means a lot if it's from an ex-Google engineer.
I mean, at this point, you're better than me at algorithms, or you certainly have like a lot more experience, or like you clearly live and breathe this stuff. So, but cool. Any last words that you want to tell the viewers or anything?
So, be sure to check out my channel because I have a lot of interesting stuff about competitive programming. So, if you do competitive programming, that's how you get really good at these type of problems. So yeah, check it out.
Definitely check it out. It's like awesome content and like super cool guy. Thanks so much, William.
Thank you.
So that's going to be it for this video. I really hope that you enjoyed the interview and that you found William's performance as impressive as I did. I mean, it was absolutely insane, really incredible performance. The fact that William is so young just adds even more impressiveness to all of this. And like I mentioned at the beginning of the video, we filmed a second Google coding interview on his channel. Go check it out. It's a very different type of question, lots of learning potential, and show him some love. He seems like a really nice guy with a very promising future. With that, don't forget to smash the like button if you haven't already, subscribe to the channel if you haven't already, and I will see you in the next video.